Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from power system stability, and the name of the topic is short circuit away from the line ends, or it is also called as fault occur at the midpoint of the parallel lines. So let us consider that this is a single machine which is connected to infinite bus through two parallel lines with the transformers. Let E dash at an angle delta E is the voltage of the generator, delta E is the load angle. This is XD dash is the reactance behind the generator. XT1, XT2 are nothing but reactances of transformer in line 1 and line 2. X1 is the reactance of line 1. Here the reactance of the line 2 is also X1, and it is considered that the fault takes place exactly at the midpoint. So therefore we will have two exactly similar reactances, that is X1 by 2 and X1 by 2. Infinite bus voltage is V at an angle 0. This will be a P delta curve for three-phase fault takes place at the midpoint. This curve, first curve, is the curve of electrical power transfer, that is pre-fault condition. Second one is nothing but PE3, which will be after fault condition, electrical power transfer after fault condition. Here by mistakenly I have written PE2, please correct this as PE3. And this is nothing but this curve will be your PE2 curve, that is during fault curve. Now let us discuss one by one in detail here. So for that case I will give here name as first is A, this will be B, this point will be C, here it will be D, here it will be E. Now what happens at point A? If you observe here at point A, this is the line PM, or you can say it is PM0 also. So PM0 will intersect this first curve. The first curve is of what? It is of PE1. So therefore here you can write PM0 will be equal to what? Will be equal to PE1. Now you can write it here PE0 also. 0 indicates what? At initial condition, or you can write instead of 0 here you can write PE1 also. That is nothing but it is the electrical power transfer before the fault. So PM0 equal to PE1. Now we know that what is accelerating power? It is PM minus PE. So as both the things will be same, you will get acceleration will be equal to 0, that is PA equal to 0. No accelerating power, so therefore speed will be exactly equal to synchronous speed, and the value of load angle delta will be equal to delta 0. Now what happens after point A, or you can say from point A to point B? Now it is observed that the fault will be takes place at point F here. So therefore as soon as there is a fault, what happens? The maximum power transfer will reduce, because whenever there is a fault there will be reduction in the voltage, and we know that P equal to EV upon X. So as your V reduces, your P is also going to reduce. If I write it here sin delta, then this will be PE. So as V reduces, PE will also reduce. Now we know relation. What is the relation? PA will be equal to PM minus PE. So as PE reduces, as here PE reduces, I write it here again, PE reduces, but PM is the constant. So accelerating power will be more positive. That is what? Here positive acceleration. So due to PA is positive, rotor will start accelerating, and the speed of the rotor will become greater than a synchronous speed. That is, due to increase in the speed, what you can write? D delta by dt, rate of change of load angle delta with respect to time is nothing but speed, which is greater than omega s. So you can say omega minus omega s, it will be what? It will be greater than 0. And delta will start increasing, and the operating point will move from point B to C along x-axis. So this was the initial delta 0. But whenever, as soon as it falls from point A to B and it moves along B to C, the delta will also try to increase along x-axis up to say delta C. Now what happens at point C? This is the point C. Now here the corresponding load angle is delta C or delta CR. That is, a circuit breaker operates when the fault gets cleared at point C. the operating point will be shifted to the what? It will shifted to point D without changing the load angle. Immediately if you see from this point, immediately it will go to this point D, but is there any change load angle? No, there is no any change in the load angle because it's a sudden change. Now it is because after the clearance of the fault, whatever maximum power transfer becomes Pmax 2, whatever Pmax 3, whatever maximum power transferred, it will become what? It will be Pmax 3. Now here there is no change in the rotor angle due to its own inertia. It will not directly or immediately change. It will take some period of a time. Now what happens at point D? This is your point D. Now what is to be observed at point D here? Now here if you observe, the electrical output power is greater than mechanical input power. Please see it carefully. This is your mechanical input. This will be electrical output. So electrical output is more compared to that of this mechanical. And from the relation PA equal to PM minus PE, if you see, okay, again I will change this as PE3 because this will be what? This will be your, we can say, post fault. So this will be PE3. So PA equal to what? PM0 minus PE3. Now as this PE3 is more compared to that of this PM0, your accelerating power will be negative. As it negative means what? Rotor will start deaccelerating. Now we can say that the rotor speed will increase from point B to C, and when it jumps to point D, speed go on reducing. Please see, B to C, if you see, the delta will go on increasing, and once your point reaches to D, what happens? Now the rotor speed will go on reducing here. Now as first the speed increases and then decreases, we get a maximum power either at point C or the point D, because if you see the speed at both the points will be same due to inertia of the rotor. So therefore the speed starts decreasing from the maximum speed, that is omega max, but still if you see the speed is greater than synchronous speed. So that's why delta will further start increasing, which is shown here, let's say, which is shown here in this direction from delta C to delta E2. Let's see what happens in between D to E, or what happens exactly at point E. So please see it carefully. From point D to E, if you see again your electrical power transfer is greater compared to that of the mechanical power. So again I will write it here as a Pmax 3 only, or PE3 only. PA will be equal to PA minus PE3. Again it will be negative. But as the acceleration is negative, rotor will start deaccelerate, or rotor will deaccelerate, and speed is reducing. But if you observe here, still your omega will be greater than omega s. Delta will be further increased, and at point E what will happen? At point E, that is here, which is shown in the graph, at point E the speed omega will become exactly equal to the synchronous speed. The speed omega will become what? Exactly equal to the synchronous speed. So therefore the rate of change of load angle delta with respect to time, it will be 0. That is, this is your equation of equal area criteria. Area under the curve will be equal to 0. So let us consider there are three cases. First one is the pre-fault condition. Whenever there is no fault, then the power transfer from machine or generator to the infinite bus will be PE1 will be equal to E dash V upon x1 sine delta 0. Where is the pre-fault point? You can say it is at point A in the graph. So you have seen here at point A in the graph, PM0 or PM will be equal to what? This is your PE1. Now from the diagram, whenever there is no fault, then how I can write a total reactance? This XD is in series with the parallel combination of this. So how I can write this? Equations will be XD dash plus XT1 plus X1 plus XT2 into XT1 plus X1 plus XT2 divided by XT1 plus X1 plus XT2 plus XT1 plus X1 plus XT2. That is, you know, if A is parallel with B, we can write A into B upon A plus B. Treat this as a equation 1, treat this x1. This is nothing but your what? You can write it as, this will be your reactance. Which reactance? You can say this is your pre-fault reactance. This is pre-fault reactance. This is what? This will be your pre-fault power transfer. Pre-fault electrical power transfer. So this is the case of pre-fault condition. Now during fault what happens? Now what we will do? We will convert this diagram into its equivalent reactance diagram. Already in the power system 2 we have studied how to prepare this equivalent diagram, or you can say reactance diagram. So therefore this is the case. This is your E dash at an angle delta E. XD dash was there. Then now as if you see, as it was like this, it was parallel with each other. So that's why one line here it goes in this direction, one will be in this direction. Then here if you see, after that again it is connected to infinite bus. So that's why it is connected to infinite bus. So this is XD dash. This is nothing but your reactance of the first line which is connected in the series. Now what we will do? We will convert first delta into star. So star means what? Let's say this is your point, suppose A, this is B, and this will be suppose your F. Okay, this is the point O. So how you will convert this XA? How to find it out? This reactance into this reactance divided by sum of all. XB, how to find it out? This reactance into this reactance divided by sum of all. XC, how to find it out? This reactance into this reactance divided by sum of all. So after that, what you will get? You will get this diagram as. So XD dash will be as it is. So this XD dash is as it is. This dot will be as it is. Now this portion has been shown here XA or XOA. After that, this is your point, suppose O. So let's say this is your point O. Then this will be your XOB or XB. So this is XB. Here this will be XOF or XC, simply you can say XC. Now what we will do? These two will be in series. These two will be in series. Now I will convert whatever this star into delta. So whatever reactance will be here, that is nothing but your reactance of the fault during fault reactance. So this will be your X2. So you should know how to convert star to delta and delta to star. So what this X2 stands for? This is reactance during fault condition. So we can write a power transfer equation associated with a fault condition. Instead of X1, which was there initially in the first case, here we have to write X2. So PE2 means what? Electrical output power during fault. X2 is the reactance during fault, and this will be equation number 3. Now next is, third case will be case C, is the post-fault condition. Now what happens in the post-fault condition? If you observe here, in a post-fault condition, this second line, whatever this second line is there, this second line will be removed, and we have only this XD dash which is in series with all the reactances. So how we can find it out? X3, we can write this value of X3 as XD dash plus XT1 plus X1 plus XT2. Treat this as the equation number 5. And what is PE2? It is E dash V upon X3 into sin delta. Mark this as the equation number 4. Now, how I can write an equation for area A1? If you see carefully, this is your area A1. So here I will write equation for area A1. What are the limits? Delta 0 to delta C. So delta 0 to delta C. Now please see this curve. This will be your area 1. So what is your upper limit? Upper limit is the line. So you can say it is PM or PM0. Lower limit is what? PE2. So I can write it here as PE2 into d delta, which is equal to what? Integration delta 0 to delta C PM. PE2 means what? Already we have derived. It is Pmax 2 into sin delta d delta. This is your final equation of area A1. Similarly, this to this will be your, this to this portion, it will be your deaccelerating area A2. So how you can write an equation? A2 will be equal to integration delta C to delta E2, or if you extend this up to this point, you will get up to delta max. This is your pi. So directly I can write equation up to delta max. So up to delta max means what? It will be this portion also. Total from this to this portion. So what is upper limit? Upper limit is the curve. This is a curve of what? PE3. So I can say it is PE3 minus lower limit is PM or PM0. So PM into d delta. So how I can write it? A2 will be equal to integration delta C to delta max. PE3 how you can write? It will be P max 3 into sine delta minus PM into d delta. So this is your equation, area A2 equation. So this is area A2 equation. Already we have written these equations here. See it carefully. This is your equation number 6 for area A1. Equation number 7 for area A2. Now the thing is that we have to find it out a maximum load angle delta max. So how to find it out this? This is your 0, this will be pi. So please see here, if you observe, this will be what? This is the point at which we will get this as a delta max. So this line, please see it carefully, this line will intersect to the same curve at this point only. This is again, please do the changes. This is your PE3. So how I can write? Can I write like this? Your PM, this line intersects this curve. Curve is what? PE3. So which will be equal to what? PE3 means what? It is P max 3 into sine delta. Okay, let me write again. P max 3 into sine delta. So can I write here value for sine delta or delta? Yes, I can write. Delta will be equal to what? Sine inverse of PM upon P max 3. So this is the answer of which delta? If you draw this line here up to this, you will get here this delta. So please see now, this to this distance and this to this distance is same. So from this total pi, suppose if I minus this sine inverse of PM upon P max 3, then whatever curve or whatever value, sorry, I will get, that value is nothing but a delta max. So this is the value of delta max. Already we have determined here. We will get this value of delta max. Pi minus, you can say delta E0, but instead of delta E0, what we can say here? This will be what? This will be pi minus sine inverse of PM upon P max 3. Now we know for the system to be stable how we can write. For the system to be stable, A2 will be equal to A1. So this is your A1 equation. So PM minus, for PE2 we can write P max 2 sine delta. So how I can write? If I substitute upper limit PM into bracket delta CR minus delta 0 minus P max 2. Now integration of sine is nothing but what? Minus cos. So how you can write? PM delta CR minus delta 0 minus P max 2, I will take it common here. Sine integration, sine integration is minus cos. So it will be what? Upper limit is minus cos delta CR, lower limit will be delta 0. So minus minus becomes plus cos delta E0. Take this as the equation number 8. Similarly, we can write expression for A2. So it is PE3 minus PM d delta. PE3 means what? It is P max 3 into sine delta minus PM d delta. So P max 3 I will take it common. Integration of sine delta, again it is minus cos delta. So upper limit it will be minus cos delta max, minus minus plus becomes cos delta CR, minus PM upper limit minus lower limit, delta max minus delta CR. Treat this as the equation number 9. Now we know for the system to be stable, how we can write? We can write A2 will be equal to A1. So that's why please equate this equation number 8 and equation number 9. So by equating equation number 8 and equation number 9, and if you rearrange the terms, all the terms in such a way that you have a cos delta CR on left hand side and remaining terms on the right hand side, then you will get this equation for your delta CR, that is critical clearing angle, when the fault occurs at midpoint. So what is that equation? Cos delta CR equal to PM into bracket delta max minus delta 0 minus Pmax 2 cos delta 0 plus Pmax 3 cos delta max upon Pmax 3 minus Pmax 2. This will be treated as your equation number 10. And already I told you what is the value of delta max, how to find it out. So delta max equal to pi minus sine inverse of Pm upon Pmax 3. So this is the very important equation. Based on that, we have to solve few numericals also. In the next video lecture, we will be able to discuss about numericals related to fault occur at a midpoint. This is the topic of equal area criteria application, short circuit away from the line end, and fault occur at the midpoint of the parallel line. Thank you for watching this video.